In the previous video, we saw Faraday's law. Now we're going to see how to apply it. We saw that Faraday's law is the change in magnetic flux with respect to time produces a electromotive force that is in the opposite direction of the original current that produced this change in the magnetic flux. So this is Faraday's law with this negative sign for Lenz's law. So we will do two examples. One is if we have here a surface, say something like this. The magnetic field goes inward the board, and here we have a axis through which we are going to rotate this surface. So the position we have theta is equal to original theta plus the angular velocity times time plus 1/2 of the angular acceleration times the time squared. We have 0 for the original angle, then 0 for the angular acceleration, and we just have that theta is equal to omega times t. So here we have the magnetic flux, that is the closed loop integral of magnetic field dot dA, the area vector, that is a vector perpendicular to the surface with length or magnitude of the area, or you can put the n here at dA with no vector. This n is just the normal vector to the surface. Well, anyway, so this is the magnitude of the magnetic field times the area times the cosine of the angle between them, cosine of theta, that is the same as cosine of omega t. Then the electromotive force is the time derivative of this, the negative of that. So it will be negative magnetic field area omega sine of omega t. Because the derivative of cosine of omega t is negative sine of omega t, this negative sign will cancel. And then we have the power is the force times the velocity, or also the electromotive force square over r. So here we will just have this square over r, that is the resistance. Another example is if we have here a circular loop, what would be the power of this circular loop with the current going? So we know that the change in the magnetic, well, for the magnetic flux would be the integral of b dot a. Here we have the magnetic field going here whatever direction we choose. So magnetic field times the area of this is pi r square times the cosine of, or put cosine theta or cosine omega t. Then the change in the magnetic field with respect to time, this would be the electromotive force, would be b omega r squared sine omega t. And then the power would be electromotive force squared divided by resistance. So we would have square b square that could be square omega r to the power sine square of omega t, and this divided by r. Another example is if we have here a surface, let's say like this, and now we will move this bar like this, with some velocity v. We're not changing the area, but we're changing the magnetic field. So let's say that the magnetic field goes in this direction. Well, no, actually we're changing the area. So the area of this, let's say that here we have some distance. This is d and this is l. So the area would be d times l. The magnetic flux would be b d l over b dl, magnetic field times the area, and the change in magnetic field with respect to time, or the electromotive force, is equal to the negative of the time derivative of this. If we divide everything by t, then we would have b l times the velocity. D over t would be the velocity. This is the electromotive force. Now, what is the magnetic force? We have force is equal to the current times the length cross product with the magnetic field. The current going in the direction of L, that is in this direction. So here we have that the force. In this case, we could say that it is perpendicular to B. So we could forget the negative. We can forget the sign value. So we just have the current times L times B. So it is this. The electromotive force is here. We have power. Power is equal to the square of the electromotive force divided by resistance, but it is also force times velocity. So we have force, that is ILB, and the velocity. So we would have ILBB, and LBB is the electromotive force. So we have that power is equal to the current times the electromotive force, or current times voltage, that we also know that. So now the current here is power over the electromotive force, but also current is voltage divided by resistance. So now we have the current here is power, that is this divided by the electromotive force, and we just have I. And then whatever we have here, we can substitute that I here for the force. So we have the power, that is ILBB, or just I times E, because well, here I'm talking about absolute values. So E is this B, L